Hi Chem Peeps. Today we're going to talk about in this video the ideal gas law and how it can be used with stoichiometry. The ideal gas law, I always tell my students, is the only gas law that's going to deal with quantity. In other words, the number of moles. So if you're given mass or moles of a gas, you're most likely going to use the ideal gas law because the N in the formula represents the quantity of the gas. We're not looking at situation 1 compared to situation 2 like we do in Boyle's and Gay-Lussac's and Charles, but rather we're looking at one gas in one situation with a quantity. Another giveaway that you're going to be using stoichiometry is that they give you a balanced chemical equation. So in this problem, we're actually going to use the ideal gas law first, then do stoichiometry, but sometimes you have to do stoichiometry first before using the ideal gas law. And I'm going to say something that's going to be like, I already kind of knew that, but students often forget. The ideal gas law can only be used with gases, hence the name. But you don't want to get tricked up because if you look at this problem, I'm going to just jump ahead real quick. It wants to know the mass of the water. And so some students might incorrectly try to solve for the moles using ideal gas law thinking it's the water. But if you look in the equation, the water is in a liquid state. If you read the problem a little further, it gives the conditions for nitrogen dioxide, which happens to be a gas. Therefore, we can use the ideal gas law because nitrogen dioxide is a gas. Another thing that I want to point out is that the ideal gas law constant, I often use atmosphere liters per mole K. That value of 0.0821 is relative to the units that are used. So for example, let's say instead of using atmospheres, you want to use torrs. Well, the constant is going to change. And off the top of my head, it's 8 point something or other. I'm going to go ahead and use atmospheres and this constant. And if you look at the problem, it gives me the value in kilopascals. So I'm going to have to convert this over to atmospheres so that I can use the constant that is also in atmospheres. So let's go ahead and convert that kilopascals to atmospheres. That means I'm going to take the relationship of kilopascals to atmospheres at STP, standard temperature and pressure, and it is 101.3 kilopascals for 1 atmosphere. And you can see the way I set it up, the kilopascals divide out, and that means our starting atmospheric pressure is 5.9. Close to the edge here. Let's fix this. I'm going to write it a little lower. 0.592 atmospheres. Another thing when looking at this, notice our temperature, and this is true for all gas laws, it needs to be in Kelvin. So coming back to my problem, I have 25 degrees Celsius. So Kelvin is going to equal to Celsius plus 273. So we're going to take 25 plus 273, and our temperature for this problem is going to be 298 K. Last thing that I'm going to show you, notice that our volume is in liters, and in our problem set it is in milliliters. Well, I think you know that 1 liter equals 1,000 milliliters, so our problem is going to use 1 liter in this problem set. So let's go ahead and solve for the moles of the nitrogen dioxide. So I'm going to use PV equals nRT, and I'm going to be solving for N for nitrogen dioxide. And so the pressure is going to be 0.592 atmospheres times 1 liter equals the moles that we're solving for times the constant 0.0821 atmosphere liter over mole K times our temperature of 298 K. Solving for N, we're going to divide both sides by the 0.0821 and the 298. So the moles are going to come out to be 0.0242 moles of the nitrogen dioxide. Now, I'm going to take this and do stoichiometry. I want to figure out, using stoichiometry, how many grams of water would be in this problem or needed. So I'm going to start with my 0.0242 moles of NO2, and I want to go to water. Well, coming up to our balance equation, I have 3 moles of nitrogen dioxide to 1 mole of water. And so I'm going to use this mole ratio to go from nitrogen dioxide to water. So 1 mole of water is equivalent to 3 moles of nitrogen dioxide. And know the moles of nitrogen dioxide, we'll cross out the moles of nitrogen dioxide. If I answered the problem here, I would be in moles of water, but they want mass. So I'm going to take off the periodic table the molar mass for water. So 1 mole of water on the periodic table, which would be 2 hydrogens, 1 oxygen, is 18 grams. And you can see through multiplication and division, the moles of water will divide out. So the final answer is going to be 0.145 grams of water. So I hope this helps you understand the ideal gas law and combining it with stoichiometry. Leave me a like or a comment if you should want more or you have a question. You can find more on gas laws on TikTok and YouTube at Kim's Chem Chat, and I will check you out on the next video.